Hi, so in this video we're going to look at more kind of elegant, if you like, way of dealing with more complicated optical systems that have multiple lenses in them. This method is called ray tracing, specifically using what's called the transfer matrix method. So this is a method that uses matrices. So before we start, I just want to have a little review of the math of matrices. If you've not really worked with matrices very much, if you've not done some linear algebra, we don't need to go into a huge amount of detail about this. There's just a couple of little matrix facts we need to know in order to do this method. So the first thing is a definition of a matrix. So for the purposes of this, a matrix is just this kind of two-dimensional ordered array of numbers. So we are only going to need to use 2x2 matrices in this method. So all our matrices are going to look like this. We've got A, B, C, D. The elements are called A, B, C, D. Sometimes if you look this method up, it's actually called the A, B, C, D matrix method. So one of the first things we can do with a matrix is we can take two matrices and we can multiply them together. Now the matrix multiplication kind of algorithm, if you like, often seems a bit arbitrary. There are solid reasons why it is like it is, but we won't go into them here. So basically the method is you take the first row of the first matrix and the first column of the second matrix, and then you multiply them element-wise. So A1 times A2 plus B1 times C2. And that gives you the first element of the resulting matrix. Then you take the second column of the second matrix. Then you switch to the second row of the first matrix and the first column of the second matrix. And then finally the second row and the second column. And you have four elements of the matrix. So the four elements of the new resulting matrix kind of contain this sort of mixed up, jumbled up set of elements from the two starting matrices. And because of this way in which this is done, one of the most important things about matrix multiplication is that it does matter what order you do the multiplication in. So 1 times 2 is not the same as 2 times 1. In most cases, there are some matrices in which it is the same. One of those is the so-called identity matrix, which is a special matrix where the diagonal elements are all 1 and all the other elements are 0. For a 2x2 matrix, that looks like this. If you have bigger matrices, then as long as all of that diagonal is 1 and everything else is 0, it's the identity matrix. And the property of the identity matrix is that multiplying another matrix by it doesn't really do anything. It doesn't change the matrix. So m times I or I times m equals n. So the identity matrix takes this place that 1 does, that the number 1 does in ordinary multiplication. So we can multiply a matrix by a matrix and get another matrix. The other thing we can do is multiply a matrix by a column vector. So if we have here a column vector called the elements x and y, we can take this matrix and multiply the vector by that. Now, it has to be in this order. It has to be the matrix times the vector. If you want to do the vector times the matrix, this has to be a row vector, not a column vector. For the purposes of this method, we are going to use only column vectors, and so we're always going to multiply matrix followed by vector. So if we do that multiplication, it's pretty much the same as the matrix multiplication, except we only have one column. So we do first row times the column and then second row times the column. So we have A1 times x1 plus B1 times y1 in the first element, and then C1 times x1 and D1 times y1 in the second element. So we created a new row vector, so it's a new column vector, sorry. So matrix times column vector equals column vector. Now that new column vector has two new elements, and the way I've written it here is one of the sort of interesting things about matrices, because if you look at this, for two column vectors to be equal, all of their elements have to be equal. So I've written this column vector equals this column vector. So if we look at that, that means that this whole thing here, the top element in this sort of sum, has to equal this. So we could write this as really two separate algebraic equations. And this is one of the main applications of matrices and these column vectors when you go into some linear algebra, because it allows you to do some elegant things, to do things like solve simultaneous linear equations, etc., by being able to write those equations as matrix and vector equations. We'll touch on that a little bit later on. So basically, matrix times matrix equals matrix, and matrix times vector equals vector. So what has this all got to do with optics? What's it got to do with rays of light? Well, the starting point for that is we are going to look at the way rays of light go through an optical system. And if you do that, you can see that at any particular point through this optical system, the ray is kind of defined by two things: its height above the optical axis and the angle it makes with the optical axis. So here it's a certain height, it gets higher or further away from the optical axis at a constant angle, then it changes angle here, it moves at that same angle at a different changing height until it reaches here, it changes angle again and propagates through. So at any particular plane within the optical system, we can define the ray by a vector. And what we're going to do is see how that ray changes as it moves through the optical system. Now, a couple of assumptions we're going to be making. The first is the small angle approximation. This is what we call paraxial optics, and paraxial optics means close to the axis. So we're assuming that all the rays are fairly close to the axis, meaning that alpha is small, so they're close to parallel to the axis. Now, often in these ray diagrams, it's going to look like they're not very close to the axis. Like this one looks like it's almost at 45 degrees here. A couple of things about the ray diagrams. Generally, in order to display ray diagrams on a small screen like this, I've had to mess with the scale a little bit. So these ray diagrams are a little bit distorted from how they would actually be in real life, if you could really see the rays of light. Generally, the size of the optical elements in something like a camera or a telescope, etc., is very, very small compared to the distances, say, to objects and images. And so that angle is usually quite small. The other thing we're going to assume is that the optical system has cylindrical symmetry, meaning that we can rotate it around the optical axis and it will always look the same. And we're also going to say that the rays are all traveling in the same plane, meaning we can take a slice through that axis of symmetry and every ray lies in the same plane. All of those things, I said, are fairly good approximations for real practical optical systems like cameras, like microscopes, like telescopes. Obviously, this method cannot solve every optical problem we might give it, but for most practical systems with these assumptions, it's good enough for designing and analyzing optical systems. So what we're going to do is we're going to take this ray and we're going to see what happens to it what happens to its vector as it translates through this optical system, starting at one end and going through to the other end. So the first thing the ray could do is just travel along in a straight line. So for instance, here we have a ray. It started with a height y0 above the axis, an angle alpha 0 from the axis, and it's traveling in this direction, horizontal distance L, until it meets some optical element in the system. So what is the new y and alpha once it gets to the end of that movement? Well, the alpha is the same. It's traveling in a straight line, so its angle is constant all the way through until just before it hits this interface. The height is really just straightforward bit of trigonometry here. We have an alpha, an angle, we have a horizontal distance L, we want to know how much higher it is, we would just use the tangent here. So L times the tangent of alpha 0 will give us that little extra bit of height. We add that to the original height, it gives us the new height. But we're going to use the small angle approximation, and because we're using the small angle approximation, that tan alpha equals approximately alpha as long as we're working in radians. So we could rewrite this equation now and say, how do y1 and alpha 1 depend on y0 and alpha 0? And if we write that out, adding in some numbers for brackets, we've got y0 times 1 plus alpha 0 times L equals our new y1. And then our new angle doesn't depend on y0 at all, so we'll multiply that by 0, and it just equals alpha 0, so multiply that by 1. So you can see right away there that that is like the simultaneous equations, matrix vector multiplication that I showed at the beginning. So we could write that translation as a matrix equation, or a matrix vector equation. Here is our input ray, y0, alpha 0. We multiply it by that matrix and we get our new ray out. And that is the basis of this whole technique, this whole method. We look at each optical element and each distance within the system as a transformation that transforms the vector, the ray vector, into a new ray vector, and perform this multiplication to do that. So let's look at another element we might meet, which is a flat interface where we move from one refractive index to another. So here we have the ray going in at alpha 0. This angle here, alpha 0, made with the normal, is of course going to be the same as the alpha 0 that the ray makes with the optical axis, as long as this is perpendicular to the axis. And this ray obviously is going to bend depending on the refractive indices, and the equation that you're familiar with is the Snell's law or the refraction law. It tells us how that ray bends. Now the ray only bends at the interface itself. It doesn't go up or down. It stays at the same height. So the new height is going to be the same. The angle is going to be different, and Snell's law, the refraction law, tells us what that angle will be. Now again, we are using the small angle approximation that lets us turn these sine alphas into alphas, and the equation becomes much simpler. So again, we can set that up as a matrix equation, because y1 equals just y0 and doesn't depend on alpha 0. Alpha 1 doesn't depend on y0, but does depend on the refractive indices and the original angle, and so that matrix becomes 1, 0, 0, and 0 and 1. Okay, so we've got translation along a certain distance and a refraction at a flat interface. There we go, back again. A more important element we're going to meet, though, of course, is a lens. And to start looking at lenses, we have to look at just what happens at a curved interface. So a spherical curved interface like this. The ray of light comes along, it hits the surface, and it's refracted using the same refraction law as the plane interface. But the important thing here is the angle between the ray and the normal. So the normal is the line that goes at 90 degrees through the point where the ray enters the new material. So our refraction law, we have to use these two angles. There's the black line there is the normal through the surface. This is our ray. So we need these two angles, which are not the alpha angles we had before. So this is our Snell's law. Right away, we're going to use the small angle approximation. So these sines are going to become just the angles. But what we need to be able to do is write these thetas in terms of our alphas. These are the angles we actually know. We need to find out how those angles relate to these thetas? Well, the first thing we can do is we can see that this normal makes an angle with the optical axis. Let's call it phi. And by a bit of geometry, this angle here equals these two angles. This is the sort of z angle identity, and then this is the opposite angle. And so these two angles are the same as this angle. So we could rewrite our thetas in terms of our alphas and this phi angle. Okay, so the phi angle is going to depend on how high up the ray is when it hits this surface. If I come down lower, this phi is going to be smaller. If I go up higher, the phi is going to be bigger. So that phi is really going to depend on my height of my beam above the optical axis. So again, we have a right-angled triangle. R is the radius of curvature of my spherical surface. This is the center of that surface. And so this y0 we can find with just a bit of ordinary trigonometry. So phi is actually going to is about the same as the sine of phi, which is then equal to the opposite over hypotenuse. The hypotenuse is the radius, and y0 is the height. So now we have our thetas written in terms of our original alpha angle, our height of the ray, our new angle, and again the height of the ray, which doesn't change. So I could plug these two thetas back into the refractive index, and I get this kind of fairly simple equation, and I can solve this for alpha 1. So now I have alpha 1, and I have it in terms of the original height of the ray and the original angle of the ray. So this is part way to having my matrix equation now. The other part is that the height of the ray doesn't change, so I just have 1, y0, 0, alpha 0. And so this is now my my matrix for refraction at a spherical interface. So ray comes in, we multiply it by this matrix, we get the ray coming out from the spherical interface. A couple of things. The R is the radius of curvature of the surface. So a big radius of curvature represents a very flat surface. A small radius of curvature represents a very curved one. If R goes to infinity, this would become 0, and we would have a flat interface. And you would see this matrix looks exactly the same as the plane interface matrix we had before. Another thing about R is that R is positive for this setup, with the center being on the opposite side, the output side of the ray. If the center is on the other side, on the same side that the ray is coming from, the curve is in the opposite direction, and this would be a negative number. Okay, so that's the one sign convention you need to remember for this radius of curvature. Okay, so what about a lens? Well, for a lens, excuse me for a moment. Excuse me. For a lens, we have kind of 3 steps to the movement. We have a ray comes in, hits the first surface, is refracted at the first surface to become a second ray. That ray then travels through the lens, where it will have a new vector with a different height. Once it gets to this point, it will then go through, we've refracted again, and we'll have a third output. So we have kind of 3 steps: a refraction, a translation, and then another refraction, to kind of model how the light moves through this lens. And those, the final output ray is y3 here, and the input ray is y0 alpha 0. So what we would need to do to calculate this is, first of all, we would take y0 alpha 0, we would multiply it by the spherical refraction matrix at this point. That would give us the ray on the other side. Then we would take that input ray and multiply it by the translation to give us the ray at the inside of the second surface, and then finally we would multiply it by the spherical refraction again, this time the other way around, going from the glass to the air, and that would give us our final ray out. So if you look at these three equations, if I take the right hand side of this one, I could substitute that in right here to give me like m2 m1 y0 over alpha 0 on the right, and then I could substitute that again. So I could do these three equations all in one go. Matrix, matrix, matrix times alpha 0. And this is the real beauty of the matrix approach, because what we've done here is we have these three matrices. We can multiply them together in series to give us a matrix for the whole system, in this case this thick lens. And we'll be seeing much more of that as we go through. One very important thing to note is that the order matters. And the order is that the matrix that represents the first thing we go through is on the right. So the light propagates through these matrices from right to left. You do the multiplication from left to right. So I would multiply 3 into 2, the result of that into 1. But M1 is the first ray, the first thing we meet, the first interface. And 2 is the second thing, which is the translation, and then 3 is the last one. So the order is reversed from the direction the light is going through, and that is common throughout all these systems as we do more and more complicated systems. The thing to remember is the first element is on the right, and light propagates through in this direction. Okay, so we combine those together and we're going to get this big set of three matrices. We could multiply these together and we'll get like a big ugly matrix. I don't want to do, like, the actual algebraic multiplication of this is kind of ugly. It's fairly simple to plug the numbers in and find just a number, but I don't want to actually do the algebra for this because it doesn't really help. A more useful thing though is to look at a thin lens, and for a thin lens we're going to take this, and you can see that to make this thin lens we just need to make this d smaller and smaller. D is the thickness of this lens. So if I make this lens smaller and smaller, this d smaller and smaller, and get to the point that d is 0, this middle one is now the identity matrix. So if this is the identity matrix, it kind of goes away. It's like we're multiplying by 1 in between. So we could just take this matrix and multiply it by this matrix. By the way, there's one small misprint here. This R should be R2 and this should be R1. These are two different R's here. The refractive index L is the refractive index of the lens itself, and N is the refractive index of the material around the lens, so air, or sometimes you could have your lens, for instance, in water or in some other fluid. So if we want to kind of multiply, to kind of work that out, this is our thin lens matrix. Okay, so most lenses can be approximated quite easily to a thin lens. And so if we know the two radii of curvature of the surfaces, we know the refractive index of the lens, we know the environment we're working in, we can work out the matrix for that lens. So we can actually simplify this little bit, and you should recognize this element is actually our lens maker's formula from the last lecture. But just to show you where that comes from, first of all, I'm going to simplify this a little bit. I'm going to call this bottom element V. Okay, so V is the refractive index lens minus surrounding divided by the surrounding 1 over R1 minus 1 over R2. So let's call that V just to kind of make the algebra a little prettier to look at. So for a lens, what we would expect for a lens is that if we were to take a ray from the focal point and we were to shine it into the lens, we would expect it to come out parallel. That's the point. That's what the focal point means. It takes all the rays from a particular point in space and a particular distance and makes them come out parallel. So we could work that out in terms of matrices. What we should be able to say is here's a ray starting on the optical axis. You see my y element is 0, so it's starting on the optical axis and it has some angle alpha 0. And first of all, we let that ray go a distance f. Let's put this ray at the focal point of the lens. So it goes a distance f. There's my translation matrix for distance f to the lens, and it does that first. And then next it hits the thin lens, which is this big matrix up here with V. This is the V. And what we should get out is a ray that is parallel to the axis, which means it's going to have a height, but its angle is going to be 0. So let's just work out what that tells us. Let's multiply these two matrices together first. So if I multiply these two matrices together, I get 1FV, VF plus 1. And then I'm going to multiply that matrix into my column vector. If I do that, I get a new column vector, F alpha 0 on the top, and on the bottom is alpha 0 VF plus 1. Okay, but this bottom element is important because this bottom element should equal 0 because we're coming out parallel. So if we look at that, I'm sorry, battery ran out mid-recording there. So where were we? Yeah, so we have we've multiplied these matrices together, and this bottom element should equal 0 for us to have this setup where a ray comes from the focal point and comes out parallel. So if you look at that bottom part, for this to equal 0, either alpha 0 equals 0, which is just kind of the obvious one where the ray is just traveling along the axis, or this bit inside here, VF plus 1 must equal 0. Well, if VF plus 1 equals 0, then that means that V must equal minus 1 over F. Okay, just solve the thing inside the bracket there. Well, V equals minus 1 over F means this over here is minus 1 over F. So 1 over F equals NL minus N, 1 over R2 minus 1 over R1. This is the lens matrix formula that we showed in the last lecture. And so our thin lens matrix just becomes 1, 0, minus 1 over F, 1. And so this is really all you need to know for the thin lens approximation. So what we have then is a bunch of different matrices that correspond to different steps within the optical system. We have the translation matrix, we have refraction of the plane at a curved interface, refraction from a plane, as I mentioned. If R equals infinity, then this is really just a special case of this. The thin lens, you could also, and I've not gone through it here, but you could work out a matrix also for reflection at a curved interface as well. I'm not going to put reflection in the matrices here because, of course, that involves changing the direction of the ray as well. Just like a little added bit of complexity, so we'll kind of ignore that for the moment. And what we have then is our this set of matrices we can use to calculate pretty much any set of rays. So let's see how it works in practice. So here's a pretty complicated optical system. Light is coming in from the right hand side in this case. So our light source is over here somewhere. Our light source is at infinity, so the parallel rays are coming in. You see they go through this first lens, through the second lens, they meet to form an image here, they diverge again, go through two more lenses, form a real image here before traveling on. So how would we treat this from the point of view of matrices? So first of all, what are our elements? Well, first of all, we have a translation matrix. So we have some distance from this, whatever we've decided is our input plane. So there's a translation matrix. Then we would multiply it by the matrix for this thin lens, if we're treating it as a thin lens, minus 1 over minus 1, 1 over f1, negative. And then we have another translation matrix for the gap to the next lens, then another lens matrix, then another gap, then another lens matrix, another translation matrix, a final lens matrix, and then a final translation matrix to the end. So if we have this whole set of matrices, which we would put them in this order with light first. It doesn't actually matter which way we draw the light going in or out of this thing. The important thing is that the first element is on the right, and then all the other elements move out to the left. We would then multiply them from left to right. So we'd multiply this by this, and this by this, and this by this. So if we have some data for this, so we know that set of lengths, and we know that set of focal lengths, we can put in any input ray we want and then work out the output ray just by doing a series of matrix multiplications. So we multiply each of those into our input ray, and we get the output ray for the whole thing. Now, this part of the multiplication, the matrices, will be the same for any ray. It doesn't matter what input ray we put in, we'll always do this multiplication of this set of, what have we got there, 9 matrices. So what we could do is we could just multiply those matrices together in the first place and create what we call a system matrix. So in this particular case, if I do that multiplication, I get this system matrix that represents this whole optical system, including the distances from the input plane to the lens and from the last lens to the output plane. So this system matrix, we could now just put in any input ray we like, and it will tell us where that ray will output on the outside. And this is the beautiful, beautiful thing about the matrix method, is that you can generate this system matrix and then just fire rays in and work out where they come out. The system matrix itself turns out to be very useful, and though I have, as I say, calculated all of these ray diagrams that I'm using in this lecture and the last lecture using a system matrix method, you only really need to do that multiplication by the ray if you're trying to draw ray diagrams and work out where the rays are going. Often, all you actually need to calculate is the system matrix itself, because the system matrix tells you important things about the whole system. And one of the most important things is which of the elements of the array turn out to be 0. So, to show you what I mean, here's our system matrix. Suppose it's the last one, it could be anything. A, B, C, D, we have 4 values. We multiply it by an input ray and we get a new output ray. And you can see that the output rays depend on the elements of the matrix. So what if, for instance, we happen to have a system matrix where A equals 0? Okay, we've done a whole load of multiplications and calculations and additions to get that system matrix, and one of the elements just ends up turning out to be 0. So what if A turns out to be 0? Well, if we look then at our column matrix, you can see that Y1, so the output height of the ray, equals element B times the input angle. So what that tells us is that the output height of the ray for this system depends only on the input angle. It doesn't depend on what height the ray went in. So what we have then is this kind of system. You can see here that if we look at the red rays are all coming in at the same angle, different heights, but they all end up at the same height on the output plane. Okay, so, and then we compare the blue ones, they come at a different angle, they end up at a different height on the output plane. So an optical system whose system matrix has a 0 in the A position, the top left position, is an optical system like this. So, for example, a camera focused a long way away, on an object a long way away, would have a system like this. Your own eye in its relaxed state is like this, because in its relaxed state it looks at distant objects, brings in parallel rays, and forms them into an image on your retina. So your own eye, A would be 0. What if B was 0? So if B was 0, now the height of the output ray depends only on the height of the input ray. It doesn't depend on the angle at all. So that would represent this kind of system. Here we have all the blue rays are coming from a certain height, all different angles, and they're all ending up at the same height on the other side. So your eye actually adjusts its focus and looks at an object close up. You're going to have a situation more like this, or a camera focused at something close up. It's going to have more this kind of system. It's going to have a matrix where the top right element is 0. Now the matrix has to include the image distance. That's one important thing, is it's only going to equal 0 if it actually includes this image distance, so the translation matrix from the image input plane to the lens, and from the final lens to the output plane. But if you have that set up, then the output height, it just depends on the input height. And actually, if you look at what we've got here, if I divide y1 by y0, A is the ratio of the heights, so that's the magnification of the system. So this matrix is telling you two things. It's telling you it's this kind of system, real object to real image, and it's telling you the magnification at the same time. Okay, so finally, the final two, C equals 0. If C equals 0, then you can see that alpha 1 equals D alpha 0. So this element tells you the output angle, and here the angle of the output ray depends only on the angle of the input ray. So we're going to have this kind of system. So this kind of system would be something like a telescope, astronomical telescope. There you look at distant objects, and you look at then with your eye into that object. And most optical systems which are designed for the human eye to look through are designed to produce an image at infinity, meaning that the parallel rays come out. That's because, as I said, in its relaxed state, your eye is focused to look at distant objects. And so if you look into a telescope like this, you will not have to adjust your eye, it'll be relaxed. So telescope would tend to look like this. Again, the ratio, the D actually represents the ratio of the angles in to the angles out, and so is the angular magnification of the system. And then the final one will be D equals 0. If D equals 0, then the angle of the output ray only depends on the height of the input ray, and so we would have this situation. Here is the input object, rays coming from a particular height come out at the other end at a particular angle. This would be something like, for instance, a microscope. With a microscope, you look at an object close up to the first element. So you take the height and you convert it into an angle on the other side. And that allows you to look into that microscope with a relaxed eye. So which of these four elements is 0 tells you a lot about what kind of practical optical system you have. So for example, I kind of summarized them in this little table here. So A equals 0, we have parallel, these are all coming in left to right, by the way. We have parallel rays coming in, forming an image at a fixed point. B equals 0, we have light coming from a close-up point ending at another point, forming a real image. C equals 0, we have parallel rays in, parallel rays out, and D equals 0, we have diverging rays in and parallel rays out. The shaded grey tells you that the matrix has to include that translation for it to work. So if we look at our system that we just calculated the matrix for, that is the A equals 0 type system. Really, because it is parallel rays coming in, forming a real point here. But our matrix didn't have A equals 0, and it didn't have A equals 0 because I calculated it all the way up to this plane, past the image point. If I had calculated the system matrix from the front lens just to the image, I would get a different matrix, this time with A equals 0. So your image distance has to include your image distance has to be included in this matrix to give us the A equals 0, the top left hand corner one here. A reminder again, in this diagram the rays are coming from left to right, in this one they're coming from right to left. Okay, that's just the drawing, it doesn't affect the system matrix. So that's kind of all very well, and you can get a system matrix, you can throw a light into it, and you can trace how rays will go through. If you wanted to, like, you don't have to do the full system matrix. For instance, if you just wanted to know where the rays were when they got to this point, you could just multiply the first two lenses and that translation distance. So you don't have to do the entire system matrix. But what you're often going to want to do is actually calculate what that image distance is. And so we can't calculate this system matrix straight away if we don't already know what is that image distance. So how would we calculate image distances using the matrix method? Well, one of the most useful things to do is just calculate the system matrix from lens to lens. So including the first and last lens, and we calculate that system matrix just from this point to this point. If we do that, we could then add on two more matrices for the object plane distance and the image distance. Okay, so they're just going to be translation matrices. And notice again the order I've done them. The object is first on the right, then we have the lens system, the system matrix, which we've just calculated for these ray lenses, and then finally we have the image distance from here to here. So we do them in that order, and what we could do is multiply those three matrices together to give us a new matrix that includes the object and image distance. So let's do that. So first I'm going to multiply this by this. Straightforward matrix multiplication. And then I'm going to take this matrix and multiply it by this one. And I get this new kind of gnarly looking matrix. And this is the matrix for the entire system, including the image and the object distances. So what if we look, so this is the new system matrix. Let's look at that system matrix and compare it to the sort of standard layouts that we just looked at. So here we've got the A dash, the B dash, the C dash, so that's these elements of this matrix. Remember, the undashed A, B, and C are the elements for just the lens system. So obviously, if C equals 0, or if C dash equals 0, or D dash equals 0, then we have an image at infinity. That's the point of these two things. So then our image distance would just equal 0. So we could look at this calculation and look and see if C equals 0, then we have this set up like a telescope. If C S0 plus D equals 0, so if this bottom right-hand element equals 0, then we have this setup. Okay, so if we have a finite object distance and we have this rule, then this will be 0, and we'll have this kind of situation, image at infinity. Okay, now if we do know that our object is at infinity, that C isn't 0, then we know we must have this situation, this top left should be 0, and so we could calculate our image distance by rearranging this top left hand and making it equal to 0. So the image distance, if the object distance is infinity, is going to be given by element A divided by element C of the lens only or optic system only matrix. If we don't have any of those three situations, we must have this situation, so this top right element has to equal 0. The B dash has to equal 0, which is this top right element. So if we write that whole thing down as an equation, make that equal to 0, then our image distance can be calculated by solving this equation. What we get is this quite nice, easy equation, which is object distance times A plus B divided by object distance times C plus D, all minus. And it's kind of easy because the A, B, C, D is in the same order as in the matrix. And so this can be used to calculate the image distance. Now, actually, this equation is the only one of those that you really need to know, because this equation actually contains, in special cases, all the other special matrices as well. So if you have A, B, C, D as the matrix for the optics, for the first lens to the last lens, so not with anything outside at all, so just the lenses and the gaps between the lenses, then the image is given by this. And you can see actually straight away that if S0 C plus D equals 0, so if the denominator of this fraction equals 0, then your image distance is going to be infinity. So that already takes care of that setup where you have a finite object and infinite image. If you take the limit of this as the object distance gets bigger, so as this SO gets bigger, this B and D become less and less important in the calculation because the SO terms dominate. And so the limit as the object distance goes to infinity is minus A over C. Okay, so only these two terms remain. So with just this equation, you can calculate the image distance from a known object distance and from a system matrix that you've calculated for a particular setup. Okay, so you can fiddle with your object distance and work that. Now, obviously, you could solve this as well. And for instance, if you wanted the image at a particular place, you could resolve this equation for SO and find out what object distance you need. Just to give you an example to show you this actually works, let's suppose our entire optical system is just a single lens, so then our system matrix is just the same as the thin lens matrix. If we plug this matrix into here, so A is 1, B is 0, C is minus 1 over F, and D is 1, then the B has gone away, we're left with just SO on the top, we've got minus SO over F plus 1 underneath. If I multiply top and bottom of this equation by minus 1 over S0, I'm going to get this, and if I solve that, I'm back to the original thin lens formula. So that's just to show you that this method works the same essentially as the previous method. The advantage is that you can, just by applying that series of matrix multiplications, you can create a system matrix for a complicated set of lenses and then put in different object distances and easily work out different image distances as well as analyze the system. Matrix multiplication, of course, is a little bit tricky to do by hand, but it's very, very easy to do on a computer. I'll be putting up an assignment doing some calculations using the matrix method in a bit. There was another thing, I can't remember what it was, so we'll leave it there for now. Okay, so that's the matrix method, chapter 18 in the book. I'll also put up some practice problems. Okay, thank you, and sorry for the interruptions in the middle of that.